Okay, so this is calculus 3. Your text, how many of you read the syllabus? Okay, so you know what the text is, right? Have you accessed it? Very easy, takes 2 minutes. Okay, just do what it says. Go to OpenStax, find math, find calculus 3. There's your book. Okay. And if you can't do that, go back and look at the instructions. I don't think you'll have any trouble, but if you do have trouble, email me. Okay. Or I can send you a direct link, but I want you to find it yourself so you know where to look for stuff. Okay. Actually, I think I might have even provided you with a direct link. I'm not sure. And generally, what you want to do is download it as a PDF. And if you like having a physical copy, you can order one from OpenStax, I think, for about $50. Okay. For a textbook, it's very cheap. It's a good textbook. Not the one I would prefer to use, but that one's out of print, and it's in your syllabus as a recommended supplement. Very good text. It's out of print, and most of the used copies that have been circulating around have eventually been bought and no longer in circulation. So it might be hard to find. It might not be. It used to be you'd get one for $5. Okay, Abe's books or whatever. So if you get one cheap, it's probably worth having and keeping, because multivariable calculus is the language of engineering more than any other course. Okay, depends on the field in engineering, and mechanical engineering by all means. Computer engineering depends on what you're getting into. If you're getting into optimization models, gradient descent, stuff like that, you need what's in this course. And linear algebra, you put it all together. There are some areas of engineering where it isn't all that relevant, but it still pops up. So you don't want to be deficient. Also, you want to be able to solve problems at this level. And that's one of the main benefits of taking mathematics and physics courses. Is learning to deconstruct, solve problems, and so forth. Okay, so there we are. That's calculus 3. That's the text. I'm not going to take time to go over a printed syllabus today because we're on short time because of the revised schedule. But the high points are you're going to have 2 or 3 tests. That's going to be the bulk of your grade. Okay. There's homework. You got to do the homework. If you don't do the homework, you're not going to be prepared for the tests. Unless you got an IQ of 160, in which case, just take a quick glance at the book. I'll give you a test and test out of it and be gone. Okay. There aren't many 160s running around out there. I've encountered a couple. And, encountered one guy whose math IQ tested in the 190s. He was smartest kid in Virginia among kids. And another one who was pretty impressive. Okay. And a lot of other bright ones that weren't quite at that level. Okay. So my point is, you got to do a lot of work. And don't get behind on it, because everything builds on everything. All right. What else do you need to know about the course? All I'm going to say now is read the syllabus In a minute, I'm going to pause the video. Incidentally, when the video is going, please don't speak or identify yourself. Don't walk in front of the camera. I might have to trash the video and not post it. Privacy laws go way too far. My opinion, other people have different opinions. They're wrong, but I get you got to respect them. Okay, seriously. Yeah, they're different opinions. I find it very inconvenient that we can't have a real class and have a recording. Okay. But I'll always pause the video if you've got a question or anything. So just let me know. I'm not looking to throw something at me, whatever. And I'll always answer your question. We're going to cover the chapters that the syllabus says we're going to cover. Okay. There is a chapter on parametric equations. You're supposed to have covered parametric equations, starting with a second semester pre-calculus, as well as, I think, in your second semester calculus course. I find that too many people come into this course not knowing that stuff. And that goes back to the fact, especially if you did a dual enrollment course, second semester calculus comes at the end of the year when the school has all kinds of distractions going on and doesn't get finished up very well. Sometimes it does, impressively well, but not everywhere, and often just because of unexpected, oh, you can't have class today, we're doing this. Yeah, that kind of stuff. It shouldn't be going on, but yeah, the high school's got to do their job too. Okay. So I'm just going to ask you right now, are there any questions about the syllabus or about the course, anything that you really want to know before we jump into some stuff on vectors? Okay, I'm just going to start in with what you need to know about vectors. And just at the level of pre-calculus, what's covered in pre-calculus on vectors. There's more, and not everybody has had linear algebra, so you don't necessarily understand orthogonal projections and stuff like that. But you'll get stuff here that'll make sense to you and actually help you with your linear algebra too. But we're not going to spend a lot of time on it because we have to be able to assume it from the pre-calculus, okay? So what we assume from pre-calculus, and I'm just going to be very brief. Vector is anything that has a magnitude in a direction. Now, officially, the magnitude is scalar. For our purposes, it's just a number. Okay. But that's it. Typical notation. It's a vector in 3 dimensions. If it's in 2 dimensions, you can leave the C off. Okay. So is everybody familiar with some of this notation? How many of you seen the IJK notation? I'll explain it if you haven't. I'm seeing dubious looks, I'll explain. Okay. This notation is fairly standard, or parentheses will narrow open. Okay. If you haven't seen any of that, be sure you let me know, because you're going to have to do some reviewing, because this course is, another name for this course is multivariable calculus. Another name is vector calculus. It's built on vectors. So if you have, not too difficult to learn the basics, but you're gonna have to use it almost right away. Okay, so be sure you let me know. And I actually made up a set of exercises that incorporate vectors into some of the basic things we do in this course. I'll be posting those. Soon, hopefully before next class. Okay, they start out very simple, but they get into some of the central concepts of the course fairly quickly. I don't think that your textbook is going to do a thorough review of vectors. Okay. I would recommend, if you haven't had it, that you also download their pre-calculus, OpenStack's pre-calculus, and do everything they have in there about vectors. Work through it. Okay. At least work through any parts that you don't know. Okay, well, typically then, a vector can be drawn with a set of coordinate axes. You can have an initial point and you draw an arrow. It stands for terminal points. Is that my computer? Could have been, because Zoom does some very strange things. And I hope it's working. Okay. And the magnitude, when you draw a picture, the magnitude is like the length. Okay. And the angle is measured relative to the positive x-axis, to the direction of the positive x-axis. Okay. So if I have a vector like this, okay, this vector magnitude, the length, direction is theta. If we do it like this, then this vector is AI plus BJ. What's this I and this J thing? I is a unit vector. In the x direction. J is a unit vector in the y direction. K is a unit vector in the z direction. If you're working in 2 dimensions, of course, you don't have the z component, you don't have j. That's okay. Okay. So you can call A, B, and C your x, y, and z components. So you multiply A by a unit vector in the x direction, B by a unit vector in the y direction, C by a unit vector in the k direction. Now, what do I mean by unit vector? I mean a vector of magnitude 1. It's like 1 unit long. Okay. So if you want to get a vector, it's 10 units long, you multiply it by a unit vector in that direction, and you get a vector that's 10 units long. I didn't say that very well, but There's a picture of your I, J, and K vectors. And of course, implicitly then, this is your y-axis, this is your x-axis, and this is your z-axis. Okay. Now, vector operations like addition, subtraction, and multiplication are simple. You can multiply a vector by a number, by a scale. Okay. So some rules. Now again, I'm doing this very quickly. I'm just trying to think of what letter to use. I'll just use D. D multiplied by AI plus BJ plus CK is DA times I plus DB times J plus DC times K. In other words, you just multiply each of these by A. It's just a distributive law. So this is just a distributive law. Now, D is a scalar, it's a number. If you are not familiar with those terms, then look it up, get that pre-calculus book or some other reference and systematically take a look at it, okay? If you add two vectors, it's just like the distributive law, okay? You add the components of I, the coefficients of I, you add the coefficients of J, you add the coefficients of K. Or if we do it in this notation, and you could translate that into IJK notation. Then might be a little hard to read. That's an A2 there. Didn't come out very well, but A1I plus B1J plus C1K dotted with AI plus BJ plus CK equals, chalk is not writing well. A1, A2 plus B1, B2 plus C1, C2. These are vectors. This is just a number. There's no I, J, K. Okay. Now, draw this in two dimensions. Well, we don't need this. Here's AI. This is some multiple of your I vector. Your vector in the positive X direction. So exactly. Here you got an X and Y axis here. Your I vectors here. Your J vectors here. Your unit vectors, they have length 1. There they are. You have AI and you have Bj. And now this vector is the vector AI plus Bj. Because when you add two vectors, we put them together head to tail. I'm not even going to explain that. Okay, that's so basic that everybody should know it, but if you don't, you'll be able to understand by looking at some pictures, okay? And by what I'm doing, because I'm going to do a lot of head to tail stuff, okay? So my question then is, what's the magnitude of AI plus Bj? It's how long the vector is, okay? From the picture, by the Pythagorean theorem, this is a right triangle because the I vector is perpendicular to the J vector. So you got a right triangle with legs A and B. The hypotenuse is the square root of A squared plus B squared. Okay. Now, if you're not real familiar with the Pythagorean theorem, I'm sure you are if you've had linear algebra. Okay. Everybody should be if they had any trigonometry. Okay. But all depends where you have your pre-calculus and you know what math you had before you had your calculus courses. Everybody's had those. Okay. But there's your Pythagorean theorem. You need to be real familiar with the Pythagorean theorem. You've been through calculus, you know it. I hope. Okay. No, that's just geometric. That's just hypotenuse of triangle. Pythagorean theorem. The other way we write that is AI plus Dj magnitude. And this is a term symbol you'll be familiar with in linear algebra pretty soon. Stands for a norm or a magnitude of, okay? And it can be used, it's not always used the same, but it's always clear what it means, okay? That's just a square root of the dot product of the vector with itself. Because if you do the dot product by this rule, you multiply I component by I component, that would be A times A. J component by J component, that'd be B times B. That's A squared plus B squared. And that gives you A squared plus B squared. Exactly the same thing you would get from the triangle. Now, that's very handy if you're working with a vector in 3 dimensions. Because if I had a CK and a CK here, I'd end up with an A squared plus B squared plus C squared. Now you can see that by doing a rectangular solid. But it's very handy because you can do it in any number of dimensions, as you will see in linear algebra. Okay? If I want to have, if I've got an 11-dimensional space, I probably won't use A, B, and C, or I, J, and K, or just A, B, and C. I probably won't use the alphabet. If you're doing high-level data analysis, sometimes you're working in spaces with millions to hundreds of millions of dimensions. Okay? But all of this can be extended to any number of dimensions. In other words, we can go to 3 dimensions just by doing a third component, okay? Or, a third component here in this notation, okay? We could do a vector A, B, C, D, E, F, G, 7 dimensions. And we could operate on those vectors, okay? So this stuff extends very readily, as you'll see in linear algebra, to multidimensional spaces. In this course, we stick with 3 dimensions. But you have to understand how 2 dimensions expands into 3. Okay. And by notation, it's very simple. In general, then, the magnitude of a vector V is the square root of v dot v dot product. Okay. In general, the dot product, which we can define just by component times component, has this geometric definition that I'll illustrate with the picture. Here we got V. Here we've got W. And here we got the angle between them. Okay. If I want to get the angle between two known vectors, it's real easy to solve this for theta. Another part of the picture. Makes a little more sense out of it. It's called a projection line, makes a right angle with V. Here's W. This distance here, or this displacement, is the magnitude of W cosine theta, isn't it? Now, again, if your trigonometry is not at your fingertips, it needs to get there quickly, okay? You can't be stumbling over basic trigonometry of triangles. You have to know that this leg of the triangle is equal to this hypotenuse multiplied by the cosine of this angle. You have to recite whatever mnemonic you learn the trig functions from. You don't have it. You don't intuitively understand it, and it's going to be harder to apply. Okay? So you want to nail this. This is just right angle trigonometry. We don't do much non-right angle trigonometry, which is the simplest part of trigonometry, which should have been covered very thoroughly in pre-calculus 2. Okay? So make sure you understand how triangles work. You don't have to do much with law of sines and law of cosines and stuff. Matter of fact, this is just the law of cosines. Okay. So you prove that this dot product has these properties using the law of cosines. It has these properties, then this has to be the case. If and only if, total equivalence. I don't expect you to prove that. Okay, I never had to prove it. And all the way through graduate school, some work toward a doctorate that I didn't get to finish. Okay. And it was no big loss to the mathematics book that I didn't finish it. Okay. Let's move along. Even after that, I'd never thought about the proof. Never had to do it. Look at it and understood it in 10 seconds, because for that time I understood stuff pretty quickly. That was pretty neat, but I never understood it until I started teaching pre-calculus. Okay. I mean, I never looked at it. I never thought about it. So you can probably get through your life without being able to prove that that's equivalent to this. Now, if I was teaching a linear algebra course, I might ask for that proof. I've taught linear algebra many times. I haven't always asked for that proof. So I don't know if you got that to look forward to or not. Either way, I've done it and I've not done it. So no fault to anybody. Especially the guy who's teaching our linear algebra, which is really great. Okay. There's another thing we do with this that I'll mention right now that's a little harder to understand, that we'll talk about in a little more detail, probably starting next time. That here's V and here's W. Here's your projection. This displacement is magnitude of W cosine theta. This little vector here is a unit vector in the direction of V. So that would be V divided by the magnitude of V. Now that is something you need to understand. If you divide a vector by its magnitude, you get a unit vector. If the vector is 10 units long and you divide it by 10, you get a vector that's 1 unit long. The magnitudes of your components are still the same. They're just 1/10 as big, but they have the same ratio to one another. Makes your direction the same. If I multiply this by magnitude of W cosine theta, then I get this vector, which is leave myself room to write it. That can be terrible at planning board space. So this vector here, compared to here, has magnitude equal to magnitude of W cosine theta. If I multiply that by the unit vector V divided by magnitude of V, I get a vector that goes from here to here. Okay. That's the component of W in the direction of V. I'll say even a little more because it's worth maybe looking at and pondering. If I then, this is going to be important in this course. I don't expect you to know it at your fingertips next time, but it's worth thinking about now because it's something people often don't understand even at the end of the course. So start thinking about it now so you can lock it in when you see it again. If I subtract this from this, if I subtract this orange vector from the W vector, what do I get? Now let me redraw it. chalk to be an cooperative. Okay, this vector, same thing I wrote here. I get a bit of surface in the chalk. If I subtract that from W, then the vector that I get is this. This is a vector W minus this, and this is perpendicular to V. Okay. So the V equals this plus this. Now, if I take this vector over here and add it to this one, it gives me W. I said V. W equals this vector plus this vector. This vector is the component of W in the direction of V. This vector is the component of W perpendicular to V. Okay? So here's a picture of components. Of W. Parallel to V and perpendicular to V. I recommend that you get as much of that into your head as possible without falling asleep or becoming psychotic. Okay? In other words, don't strain yourself to give this a little thought, and then maybe a couple of days later, a little more thought. Because it's central to some stuff that we do in this course. It's built on just these very basic ideas of vectors. Okay? And not sure all of that was visible on the screen, but there it is. Okay? So again, just by this, we can use component times component plus component times component to calculate the dot product. If we know the components V and W, we can now figure out how much of W goes in the direction of V, and we can make a vector in that direction that we can subtract from W to get the component perpendicular. Personal jet plane, and you're flying in an arc, a circle. You might be accelerating, you might be speeding up, you might be slowing down. Okay? You have an acceleration vector in the direction of your velocity. That's what speeds you up or slows you down. Okay? You have a vector perpendicular to your velocity. That's what changes your direction. That's what gives you a centripetal acceleration, which you feel as a centrifugal force. And if you turn too fast, it smashes you against whatever side of the cockpit you're accelerating in opposition to, bad sentence. Maybe makes you unconscious. Maybe makes you lose your jet. Maybe makes you lose your life. Pilots know this stuff. At least people, they turn loose in jets. Okay. They're often engineers, especially people that fly them. That's what I think. I don't know. Especially, I think most astronauts are engineers. Yet again, I don't have statistics on that. Okay. That's a little bit complicated, but it builds up on your basics. Okay. So there's also the cross product. And I'm going to give you the rules for the cross product. Seeing if I have enough board space and I can do it here.
Hey everybody, a quick question. Thank you, Jason. Thank you for doing this as well. My question is anything and I'm going to see it. It's my office. Does anybody have a good way of generating? Remember how we used to get that in the groceries with the flip redirects and stuff? Does anybody have a good way of doing that quickly? And
Okay. People out over there, but I'll leave the door right. If anybody finds that disturbing, let me know and I'll ask them to turn it down. Okay, doesn't bother me that much, doesn't really show up much in the videos. So short of that, they're doing good stuff. Okay, now this says I, right? This is I, J, K. This is 0 vector K, negative J. Okay. And I'm sorry, this chalk isn't writing very well. And of course, I'm not necessarily helping, but let's see if I make a real estate. And then hold on. Yeah, J cross K is I. Yeah, J cross I is negative. You've got the right hand rule on this, and if you don't know the right hand rule, I'll tell you. Okay. Let's take I cross J. I's in this direction, and you kind of want to be looking. Okay, I's in this direction, J's in this direction. I take my fingers of my right hand, put them in the direction of I. Turn my fingers toward J.
yeah,
My thumb points in the direction of I cross J, which is the K direction. Okay. So I cross J equals K. Convince yourself that I cross K equals negative J. See if you can do that. Okay, get in. Okay, now, okay. It's not clear what you have to do. Yeah, okay. You just did it.
Okay.
Yeah, that was a good start. You started with this and that didn't work. Please don't speak. while the thing's on. Okay, but yeah, that was very good. You started this, no, it's not gonna work. Then you said, okay, yeah, if I do this, then I can turn my fingers toward K and you've got it. And you've got it, okay? So make sure you've got it. You know, these just come from that. Okay? So these are all really simple. And you can always write out the list. Um, Now, I say that I cross I is 0 because if your finger's in the direction of I, you can't turn your fingers toward the direction of I. Okay? Now there's another definition, but any vector cross product with itself is 0. Okay? That's not times, that's cross product. Okay? The cross product of two vectors, any two vectors, V and W, like A1I plus B1J plus C1K, cross product with A2I plus B2J plus C2K, like the vectors I've got over there. But in the case of the cross product, it has this magnitude and direction perpendicular to V and W, but there are two directions perpendicular to any two vectors. Okay? If I've got, and I'll demonstrate this and everybody's looking, go ahead and write it down. Okay. If I got a vector in this direction and a vector in this direction, okay? See how my arms are? My arms are vectors, okay? I got to turn my palm this way to turn this direction toward that direction, right? There is the direction of V cross W. This cross this. If I did W cross V, then I'd have to have my hands reversed and this hand would be upside down, it would be down. Okay? The vectors V and W, and this is an important image here, okay? Watch while I wave my arms. I've got the camera focus kind of tight, but my arms kind of, if I keep them in the same plane, you see if there's a plane that kind of cuts this way, okay? This vector is perpendicular to the plane, so is this one, okay? That makes sense? So it's a way to get a vector perpendicular to a plane. It has a lot more to do when you get into electromagnetism and mechanics of materials and all kinds of stuff. You get a lot of stuff built on this idea. Okay. So I say the direction is perpendicular to both V and W. And you choose which perpendicular direction by the right-hand rule. Okay. Now, calculate A1I plus B1J cross product with A2I plus B2J. All you need is a distributive law. Always figure out what they are, right? And you should. So this cross product I can write as A1I cross A2I plus A1I cross B2J. Okay, just multiply A, or taking the cross product, this crossed with this, plus this crossed with this, right? It's like a distributive law. It is a distributive law. Okay, now I'm just asserting it, and the deeper proofs and connections and stuff come later. So there are four things I get here. Just if I was multiplying A plus B times the quantity C plus D, I would use a distributive law, right? Well, it works the same if I've got I and J components of the vectors. Okay. Now this works out very simply. I'll write up in more detail than I probably need. Algebra allows me to do this. In other words, A1I cross A2I, I can factor out the constants A1 and A2, and I have then I cross I, right? It's a fairly straightforward rearrangement. Does it make sense? It's I'm rearranging the order of the factors in a product, essentially. Okay. And then I would have A1, B2 on I cross J, wouldn't I? I've got A1, B2, and I've got I and J, right? Cross product doesn't do anything. They're just plain old numbers like A1 and B2, okay? These are just numbers. I and J are the vectors. So I just isolate the vectors and do their cross product, and the constants I just factor out and treat just the way I would in any algebra situation. So you want to look at that until you understand it, because it'll, again, help you avoid some confusion. Okay. Now I've done the same thing here and here. I've got a J cross I, and I've got constant terms B1 and A2, scalar terms. And here I've got a J cross J with scalar terms B1 and B2, and I just rearrange the order of each of these, okay? Now, please, I can't post this publicly if people are talking, okay? So if you have a question, let me know, because I'll just walk up here. Okay, so somebody want to tell me what I cross I is? 0. Okay, because I is in the same direction as I, you can't turn anything. So does J cross J. So we're going to have 0 here and 0 here. What's I cross J? Well, I cross J is K. And this thumb doesn't quite straighten out. It's very weird. It's just some handwriting. Crazy stuff. So it's A1, B2, and J cross I Uh-oh, something's wrong. No, never mind, nothing wrong. So I cross J is K. And yeah, J cross I is this. So you end up with this. Okay. Now, yeah, there's another way to do a determinant usually, or do cross product using determinant. Is do J cross I, how do you hold your hand? You gotta be able to turn J toward I, right? If I'm here, I'm turning it, I have to turn it this way, see, unless you're double jointed, and this doesn't work for double jointed people. Okay, so you gotta turn your fingers toward your palm, you just turn your hand upside down. J crosses I and you get negative K. Okay? I kind of did that, but I was doing something else at the same time. Okay, so my point is, there it is. In general, you're gonna end up doing a determinant like this. And that's gonna equal I times the determinant V1, C1, V2, C2. And hopefully you've seen determinants. If not, you're gonna see them pretty quickly in linear algebra. If you haven't already had it. Then it's gonna be minus J times the determinant A1, C1, A2, C2. Plus K times the determinant A1, B1. And just making sure I'm not messing this up. And to do the determinant you get for I, you take the column of I and the row for I, and you throw them away, and the determinant here is what's left, okay? And you do the same with J, you throw away this column and this row, the column below J, the row across from J, you make it negative, as it kind of alternates, and you'll see a more general rule. But then K, you do the same thing, and that's how you get all this. And then, then this determinant is just this minus this, B1, C2. Minus V2, C1. It's real easy to do these wrong as a one. Okay, especially when you're running them out. A1, C2. Minus A2, C1 plus K times A1, B2 minus A2, B1. And notice that if C1 and C2 happen to be 0, then both of these end up 0. Okay. When I did this cross product, I didn't have any K components. So my C1 and C2 were automatically 0. Okay. So if I replace the C1 and C2 by 0, I have this cross product. And notice that this agrees with this. And these two aren't going to be there. Okay. Well, that's a fair amount about vectors. Okay, and that's stuff that, most of the stuff I expect you to know already up through dot product. Okay, now this thing that we did here with dot product, I don't necessarily expect. But I recommend you take a look at it. And there's a lot of other stuff that I didn't say. We're gonna start using vectors immediately. So, digest as much as you can, depending on what you've already said.